Okay, so starting unit two, will be on aldehydes, ketones, and carbohydrates. All right, the chemistry of carbohydrates is really the chemistry of aldehydes and ketones. That's why we're doing these together. Okay, a carbonyl group is a double bonded oxygen to a carbon. Um, we talked about these a little bit when we were talking about the oxidation of primary and secondary alcohols. But this will be a formal unit on aldehydes and ketones, including naming, structures, and of course, reactions. Now, the tricky part of unit two is there's two bundles of reactions. Um, and the second bundle is the trickier of the two, which is the main chemistry, by the way, of carbohydrates, is the second bundle of reactions. Okay, so an aldehyde is on the end. Only. Ketones are in the middle only. The simplest aldehyde is formaldehyde, and we're going to see um, aldehydes are unstable, so they react very quickly, where ketones are more stable, and hence they don't react as easily. The simplest ketone is acetone or propanone. Okay, so naming an aldehyde is going to be aldehyde. And of course, the backbone is going to be on the longest carbon chain, including the aldehyde group. So I gave this as an example before. Let's do one real quick. Okay, so what's the longest carbon backbone that includes the aldehyde group on the end here? Well, for sure, it's going to be this here. And it looks like we can go either way, left or right here. So let's just go down. In the functional group, we'll start the numbering. Okay, so this is a 6-carbon backbone with an ethyl branch on carbon number 4. So it's going to be 4-ethyl hexanal. So is it really very similar to alcohols? Um, as the um, mass of the aldehyde goes up, the boiling point follows it. Aldehydes are intermediate between um, alcohols and intermediate between um, ethers and alkanes. So, and the main difference is it's got an oxygen, but it's got no hydrogen bonding like alcohols. So this hydrogen bonds to the carbon, not to the oxygen. That's why it's not hydrogen bonded. Okay. Ketones is the carbonyl group is in the middle someplace. And again, the longest chain has got to contain the ketone. By the way, cyclic ketones are common. You cannot have a cyclic aldehyde, however, because an aldehyde requires a hydrogen attached to that carbon there. And on a cyclic one, there's no room for the carbon, excuse me, no room for the hydrogen. Okay, so this little short reaction I've got here, cyclic ketones come from secondary alcohols, and this is a secondary alcohol right here. Okay, so let's do one of these. And let's put it here. Okay, so we've got to include functional group on the backbone. So that means that's for sure. Now the next question is if we go to the right or the left. Well, if we go to the left, it's got 2 carbons. If we go to the right, it's 3. So we're going to go to the right. I'm starting this end. So ketones cannot be on the end. So this is a hexanone. My ketone, it's on the end, ONE, and then we have an ethyl on carbon number 3. So that's 3 ethyl, 2 hexanone. Now with aldehydes, we don't have to say 1 hexanal because by definition they're on the end, which has to be carbon number 1. Now if you want to put a 1 in there, that's fine. Okay, and like aldehydes, as we increase in boiling point, goes mass. Bigger the molecule, higher the boiling point. Okay, so the only intermolecular forces in a ketone is going to be dipole to dipole and London dispersion forces. No hydrogen bonding. Okay, so you'll notice here boiling points. The alkanes, the lowest, the alcohol is the highest. Alkanes, alkenes are the lowest. Alcohols are the highest. And aldehydes and ketones are kind of in the middle. Similar to ethers, similar. Now, because the electronegativity of the oxygen is pretty high, it still has a dipole moment to it. So this is going to be partially negative, the oxygen, making the carbon partially positive. So in water, you can have hydrogen bonding between the oxygen and the hydrogen in the water. So because of that, alcohols excuse me, because of that, aldehydes and ketones are water soluble. Now they could have a long tail, a non-polar tail, which would overcome that polar carbonyl group. Okay, so we've gone over naming. Now let's get into reactions. Now this is a review reaction from Unit 1. Okay, we've got two hydrogens here on a primary alcohol. That means it can be oxidized twice. A secondary alcohol has got one hydrogen there, so we can be oxidized once. So to derive an aldehyde, we have to start with a primary alcohol. To derive a ketone, we have to start with a secondary alcohol. And because there are no more hydrogens here, it can't be oxidized any further. Tertiary alcohols have no hydrogens there at all. Now, our wet lab today and Wednesday is going to be involved with alcohols. And we'll be doing a lot of these oxidative reduction kinds of things with alcohols. Very similarly, aldehydes and ketones are also involving similar type reactions. Okay, now aldehydes, as I said before, are more reactive, more unstable than ketones. Okay, so there's an oxidation reduction reaction called Tollens and Benedict's. Now you're going to have to know these because we're going to be using these reactions both in this unit and also the carb unit. So this is an oxidation agent here, which is potassium dichromate. And in these test tubes, we have ketone in the middle, acetone, and an aldehyde on the right here, benzaldehyde. Okay, when we put the oxidizing agent into each one of these, there's no color change in the middle, means the ketone was not oxidized, and there was a color change with the aldehyde. So no color change, color change. That means the oxidizing agent is reduced. And when it's reduced, it changes color. Now, this is the reaction. Now, I've simplified this. Instead of saying silver amine, I've just said silver ion, because the ion is what reacts, and the NH2 is just a spectator ion. It needs to be an alkaline base. So here is where the aldehyde is oxidized to the acid, salt, and it's salt because it's in a basic environment. And the silver is oxidized to the metal. And this is a spectator ion, just as these guys are spectator ions. So you need to know this reaction. Now, we can do an example. Let's take 1, 2, 3, 4. So this is butanal plus silver ion. in a alkaline or basic mixture. And what's going to happen is the silver is going to be oxidized to silver metal. And the aldehyde is going to be oxidized. So over here, we're going to have acid salts. And we're not going to have to name that till next unit, unit 3. Okay, so that's an example. Now what happens is this, because it forms silver metal, ends up turning the inside of the test tube mirror-like. It's a very cool reaction. Now, the cool thing also about this reaction is this is how they fix antique mirrors. Because antique mirrors were silver plated on the back to give the shininess to make it into a mirror. And frequently along the corners of antique mirrors, the plating comes off. So what you do to restore the antique mirror is you do this reaction here. And you end up plating the silver metal onto the glass of the mirror. It takes about 2 minutes to happen. And by the way, this is also how you check for a certain kind of carbohydrates. There are 2 kinds of carbohydrates. There's something called a reducing sugar and a non-reducing sugar. And this is the test, one of the tests used to determine if it's a reducing sugar or not. The other test is it's exactly the same reaction, only you're using copper rather than silver. So this is one of the tests you're going to test for whether there's a ketone or not. Ketones, as you know, cannot be oxidized. Aldehydes can. So this reaction will go to either this color or this color. Depends how strong the aldehyde concentration is. Now, there's one exception to the ketones, and that's if you have an adjacent OH group next to the carbonyl. This will give a positive reaction. That's the only exception. Okay, so let's do an example of this one here. Okay, so let's do the same 4-carbon butanol plus copper plus 2 in an alkaline environment, basic environment. We end up with the acid salt again, and the copper is reduced to copper plus 1. And this is the orange color because it forms copper oxide. That's Cu2. Okay, so it goes from a +2, +1, and that's not an H there. That is 1. That's reduction. And this is being oxidized. And this is called Benedict's solution. So again, you need to know these two reactions. Now, we talked a lot about oxidation, 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 and aldehydes can be reduced. They can be reduced with hydrogen gas and a metal catalyst. Normally it's platinum, but it can be other metals as well. Nickel will do it. What else? Chromium will do it. A number of them, but frequently they use platinum because it's expensive, but it doesn't ever go away. The other ones pit after a while, and you can't use them. So that's why everyone likes to use platinum. But um, so to reduce the aldehyde to its primary alcohol, we're going to take hydrogen gas, metal catalyst, and it'll reduce it, the aldehyde, to primary alcohol. If we oxidize the primary alcohol, we end up with the aldehyde. Same with the ketone, it goes to the secondary alcohol, and we can oxidize it back to the ketone. So this is one way to make an alcohol, is you reduce aldehyde or ketone, or you do an addition reaction of an alkene to get an alcohol. Okay, so that's the first group of reactions, oxidation reduction. And that is going on here. Okay, so this is the reduction. There's the oxidation. Now, this is the second set over here. Of reactions. And if you add an alcohol to a ketone or to an aldehyde, you get something called a hemiacetal, or a, let's see, hemiacetal or a hemiketal. And then with the continuation of an alcohol, if it's available, these go to an acetal and a ketal. I don't know why the Y is there. Okay, so excuse me. We talked about ethers being COC. If we have OCO, then we have one of these acetals, ketals, hemiacetals, or hemiketals. But these are the three steps I've invented this flow chart to determine what you have. Okay, so let's so for example, now the next set of dry labs are under you go to files, unit 2, worksheets. You'll see the worksheets here for aldehydes and ketones. And they give you lots of practice. These are going to be similar to the ones you've already done in unit 1. Okay, so now here we're going to have 2 backbones. You're going to have a primary backbone and a secondary backbone. Okay, so in this case, we're starting with an aldehyde. So the aldehyde is going to be the primary backbone. I'm going to add to it an alcohol, which is going to be secondary backbone. So what's going to happen is the alcohol is going to attach here. And the second time, it's going to attach same carbon there and replaces the OH. So let's look at this now. Number 1, let's look at the middle one first. Okay, so how do you determine whether this is a hemiacetal or an acetal or nothing? Okay, step number 1 is we have OCO. That's a yes. The next one is we look to see if there's an H there. H present. Yes. Okay, if an H is present, that means it's a hemi something, hemiacetal or hemiketal. Acetals come from aldehydes, ketones come from ketones. Step number 3 is there an OH present? Okay, and there is an OH present. Okay, so if we answer yes to number 1, we have something. If there's an H present, that means it is an acetal, not a ketal. If OH is present, it's a hemi. So what we made is a hemiacetal. So we have OCO, yes, H, yes, OH, yes. Okay, the H means we started with an aldehyde. Over here on the left. Okay, the OH means that we've done this once. If there's no OH present, that means it's gone ahead and reacted with another alcohol. It could be the same alcohol or a different alcohol. Now we're going to find with carbs, the first alcohol is and the second alcohol are different. And that's how the um, uh, small sugars are linked into a bigger sugar is through this reaction right here. And I'll show you that on Wednesday. Okay, so let's do this one now. Okay, so we're going to go. We have OCO is yes. Is there an OH present? No. Is H present? Yes. Okay, so with no OH, that means it's not a hemi. Y is present, that means it's an acetal, not a hemiacetal. Now you're going to have to practice this. And that's why I invented this little flow gimmick. Now, over here I mentioned an anomeric carbon. Anomeric carbons are where the original carbonyl group was located. And that anomeric carbon doesn't change. Now, the anomeric carbon, when we get into carbohydrates, is going to be really important because that's the location where the rings open and close at that anomeric carbon. Okay, so this is the tricky part of this unit, are the acetals and the ketal reactions. So the OH makes it a hemi, and the H makes it an acetal. So it's a hemi acetal. Here we have an H, which makes it an acetal, and no OH, so it's not a hemiacetal, it's just a plain full acetal. The hemiacetal carbon is also known as the anomeric carbon. That's the verbiage that carbohydrates use, so I'd like to continue it. So that those red dots are the anomeric carbons. So when this breaks up, this H goes over there, and this here goes over to the carbon. So let's do practice here. Okay, so let's start with this guy here. So this is a butanal. Now, when you're running these ALs versus OLs, make sure that you you distinguish between the A and the O, because sometimes people's writing, like mine, for example, I'll write a sloppy A and it looks more like an O than an A. So just be careful when you're writing the endings here, the AL versus the OL. Okay, so we have an aldehyde, and let's throw in an alcohol. Let's do ethanol. So, all right, so this is going to be the anomeric carbon. So what happens now is this splits right here. And then this is going to go here. And this is going to go there. Now we don't have to name these acetals and ketals. Okay, so if we continue and still have an alcohol around, uh, this reaction is going to continue. Now this is an OCO, so that's a yes. And do we have an H present? Yes, there's an H right there. And do we have an OH? Yes, so this is going to be a hemiacetal. So let's continue on and add more ethanol. And Oh, by the way, I meant to. So primary backbone, secondary backbone. Secondary backbone, primary backbone. So a primary backbone is 4 carbons long. And we still have the ethanol there. But this ethanol now is going to be I drew an aldehyde. Okay, so this guy is going to go attack here, and the age is going to go there. So we're going to end up with and then our anomeric carbon has not moved. So let's do a test. OCO. We have OCO. So that's a yes. We have H present on the anomeric carbon. Yes, there's an H there. And do we have OH? No. So this is going to be no hemi. And H means it's an acetal. So this is a hemi acetal. Oops, excuse me. It's a plain acetal. No hemi. Okay, now when we get to carbohydrates, these reactions are all reversible, meaning that we can take a hemiacetal and reverse it, and we'll end up with an aldehyde and an alcohol. When we reverse this hemiacetal reaction, we end up with a aldehyde. That aldehyde then can be oxidized. Because remember, aldehydes can be oxidized, they can combine with alcohols, they can be reduced. So because they're unstable. And this is where, like we had glucose here, glucose has a hemiacetal in it. So when it opens up to an aldehyde and an alcohol when it's in its straight form. And now that can be oxidized. So that becomes an reducing sugar. I'll go into this in total detail on Wednesday. Main thing is they're reversible. Now, the reason why this reaction continues is because the hemiketal is semi-unstable. Although with sugars, the hemiacetal and hemiketal are more stable. Okay, so this reaction here involves a ketone. This reaction here involves an aldehyde. Now notice the second step requires an acidic environment. Okay, so we're starting with a ketone, anomeric carbon. I put a red dot with like I did before. And the reaction is exactly the same, except the anomeric carbon doesn't have an H by it. So when we do a flow chart here, we have, that's a yes. We have O, C, O. Is H present? No. And is OH present? Yes. And that means this is going to be, because this is no, that means this is a ketal. And with OH present, it's a hemi. So it's a hemi ketal. When we do the analysis of this guy over here, we have OCO as a yes. Is H present? No. It means it's a ketal. Is OH present? No. That means it's not a hemi. So it's a plain old ketal. Okay, so let's do an example here. Okay, so let's start with a ketone. So this would be 1, 2, 3, 4. This is going to be a butanone. And let's throw in ethanol again. Oops, I keep doing that. Okay, so we have ketone plus an alcohol. So the H goes here, and then this goes there, and that's the anomeric carbon. So this is going to be our primary backbone, secondary backbone. So primary backbone, so this is the hemi ketal. Okay, and then we continue this now. Let's do an analysis here. So we have O, C, O is yes. And do we have H present? No. Talk about this anomeric carbon right there. And do we have OH? Yes. So we have a hemi ketal. All right, so let's add ethanol again with a little bit of acid. So we have our backbone and our anomeric carbon is right there. And now this is going to add over by the OH. So let's do our analysis. OCO is yes. H is, there's no H. And there is no OH. So with no H, it's a ketal. Oops. And no OH means it's not a hemi. So this is a ketal. And again, these can be reversed. Now, let me show you where carbohydrates come into play here. This is a Benedict's reaction. Okay, so let's draw glucose. Okay, so this is glucose. This is going to be one of the sugars you're going to have to know, structure-wise. Now, we have an interesting setup here. So let's analyze this. Are there any OCOs present? Yes, that is right here. And that means this is the primary backbone. Now, what we're going to do, let's see, let's analyze this. So yes, H present, yes. OH present. Yes. So this means it's an acetal, and this means it's a hemi. So this is a hemi acetal. Now, hemiacetals hemiacetals can revert back to their original aldehyde. So order meter. Okay, all right. So this being a hemiacetal can open up to the aldehyde. So OCO is no. There is no OCO. So that means it's not an acetal or a ketal. But notice it opens up to the aldehyde, and aldehydes can be oxidized. So the point where a sugar opens up and exposes the aldehyde, it's susceptible to oxidation. So you can do a reaction where you can have sugar and you pour in concentrated acid. And when the sugar opens up, it's immediately oxidized very swiftly in a concentrated acid. And you end up with this giant amount of carbon because it oxidizes everything. It's a pretty wild reaction. But it's only because this sugar can open up. If the sugar opens up, it's called a reducing sugar. So on a test, if I ask you if this is a reducing sugar, you look for the hemiacetal. If a hemiacetal is present, that means it can open up. That means it's a reducing sugar. Okay, so just in general, a hemiketal has to have an OH and a another uh, oxy group attached to the anomeric carbon with no hydrogen. It's got to be carbon, carbon. A ketal has two of these groups attached. And these are the tests. So OCO, OCO, H, no, that means it's going to be a ketal. And there's no OH. So it should be, in this case, it's an H, so it's going to be a hemiketal. Here it's OCO, yes. No H, that means it's a ketal. and no OH, so it's a plain old ketel. Okay. Um, OCO, yes. So we have a primary and a secondary backbone. The primary backbone goes through the anomeric carbon. The secondary one does not. That's comes from the alcohol part. Okay, so let's look at this. So OCO, yes. No H, that means it's going to be a ketal. And OH is present, so it's going to be a hemi. This one down here, OCO, yes. OH, no, that means it's no, not a hemi. And there's no H, so it's a ketal. Okay, so again, this is sometimes a molecule, if it's long enough and has an OH on the end of it, or towards the end of it, it'll actually can loop around and form this aldehyde alcohol reaction and form the hemi ketal here. So we have, and the anomeric carbon is always carbon number one. Okay, so we have OCO around the anomeric carbon. As long as there's 6 carbons or longer. Let's see, let's put that over here. Okay, so OCO, OH, yes, that means it's a hemi. And H present, that means it's an acetal. Okay, so that means either this came from an aldehyde or it can be reacted to an aldehyde. That's what the double arrow means. Now, because it's a hemiacetal, it'll accept another alcohol. Now, in the case of carbohydrates, the other alcohol is another glucose molecule, because glucose is carbohydrates are polyols. So they have lots of OH groups that can react in these reactions. So let's analyze this. We have OCO. We have H is present. And we have OH is no. So that means this is a acetal. Okay, so I already mentioned this. We can go back and forth. So it'll work on acetals and also ketals back and forth. Okay, so this is where it lies on the flow chart. Okay, so this is a good stopping point. And now on Wednesday, I want to review this part here, this aldehyde going to a hemiketal, excuse me, aldehyde going to a hemiacetal and an acetal, and also the ketone going to a hemiketal and ketal. All right, so that is it for today. Um, Now this is why getting behind in this class is so hard to catch up because we still use all the old reactions. Okay, regarding the pre-lab. So your pre-lab, one, I have videos on this already. If you go to, let's go there for real quick, and then I'll talk some more about this. So if we go to modules, and we go to lab related, here's where the pre-lab comes in. It's on this video here. So the pre-lab you're going to need to have for today, or I need broom. By the way, this is a brand new sugar substitute. It's a big deal. Okay, so the pre-lab. You need one, a title, purpose, first aid of any chemical used, procedure, materials. This is the pre-lab. And you're going to do the lab, and you're going to collect data, observations in this case. And then this is, and then you're going to do post-lab questions and a conclusion. This is at home. This is in the lab. This is at home. Okay? Does that answer your question? Yes. You cannot skip a wet lab or make it up. You have to show up today. You can be there without your lab coat today. Okay. Any other questions?
Professor,
Yeah.
So if we have Wednesday lab, we don't show up for this lab though, right?
Correct.
Okay, I got you.
Yeah, you show up for Wednesday lab.
Okay, I got you. Thank
Sure. Okay, anything else, you guys?
If we decorated our lab coat, should we bring it in today for the extra credit or at a different lab?
Do you have Monday or Wednesday?
I go to the Monday one.
Okay. Yeah. I need to see if I have an assignment where you click on it and upload a picture of it. Um, Let me just check real fast. Okay, I'm gonna create an assignment right now, and it's gonna have, it's gonna be for your lab coat. And then what you do is you click on that, and
But we don't need to have our lab coat for the lab today.
huh?
We don't need to have our lab coat for the lab today.
Yeah, you need to bring it.
Okay.
It'll be worth 10 points. And this is good to do because in case you miss a wet lab that you can't make up, this will you can use this as a substitute for it. Okay. Does that make sense?
Yeah. Thank you.
Sure. Okay, anything else?
Yes, Professor, a question.
Yeah.
I need help visualizing how you drew the structure for when you added butanol and ethanol together.
Um, I'm not sure your question. Say again.
I had a hard time visualizing how you drew the structure from butanol adding ethanol.
Are you going to be in lab today?
I'm Wednesday lab.
Um, I'm going to review this again on Wednesday.
Okay.
And meanwhile, go ahead and review the video from today,
Mhm.
and then we'll go over it again. Basically, you've got the aldehyde or ketone is the main backbone, and then the alcohols stick on it. And where they stick is where the carbonyl group is. That's the anomeric carbon. In a nutshell, that's what it is. But look at the video again, and then on Wednesday, I'm going to review this again. Then we're going to get into the carbohydrate version of this.
Okay.
Okay?
Thank you.
Sure. All right. See you guys later.